A number of radioisotopes have an important role in medical diagnosis. Here a physician injects a dose of Tc-99m using a shielded syringe. Tc-99m is one of those important radioisotopes. It has a half-life of about 6 hours and it is typically extracted from a molybdenum Tc-99m generator, with the parent isotope molybdenum-99 often produced in a cyclotron. A generator is needed because of the relatively short half-life of Tc-99m. The mother 99 molybdenum with an atomic number of 42 has a half-life of about 66 hours, which is sufficient to transport it to a hospital and use it for about a week. The diagram at the top right shows that molybdenum-99 decays via a series of 3 decays. First, there is a beta decay into the isomer Tc-99m, which then isomerically transitions to the Tc-99 ground state via mostly the transmission of the 140 keV gamma ray. The ground state of Tc-99 then decays via a further beta decay into ruthenium-99, which is stable. This last decay has the relatively long half-life of 2.1 times 10 to the 5 years. The partial level scheme shown on the left illustrates that this is not the only decay path. Molybdenum-99 with an atomic number of 42 can transmute to technetium with an atomic number of 43 via 3 different beta decays. The most important one, proceeding with a fraction of 81.8%, decays into the excited state of 142.7 keV of Tc-99. This isomeric excited state of Tc-99 has a particularly long half-life of 6.01 hours because its transition to the ground state of Tc-99 requires that the structure of the nucleus changes considerably. This complicated structural change of the nucleus proceeds typically with a fraction of 99% via the initial emission of a very low energy gamma ray of about 2 keV into the excited state 140.5 keV. From there, with a fraction of 89%, the nucleus then decays into the ground state and emits the medically important gamma ray of 140.5 keV. It is this gamma ray that is used in the medical imaging applications. The remaining fractions of the transition to the ground state of Tc-99 proceeds via internal conversion, IC. The much less common competing gamma ray has an energy of 142.7 keV. How many of such gamma rays at 142.7 keV are observed on average in 100 molybdenum-99 beta decays? A common use of Tc-99m is in single photon emission computed tomography, SPECT. A typical hospital setup of a SPECT detector is shown on the left. Different image processing approaches are possible. One such approach is sketched at the bottom left. In this approach, the 140 keV gamma rays from inside the patient are directionally collimated using an array of LED collimators. The geometric parameters A, B, C, D and the thickness T of the LED collimators then determine the resolution of the instrument. The medical applications of the technique are manifold. Imaging the blood perfusion of organs in the human body is one of those applications. As just one example, the images on the right show SPECT evidence of reduced perfusion in a brain, which can be used to aid the diagnosis of mental health issues. Looking at the images, it is clear that in this particular brain, the blood is not flowing uniformly throughout the brain. The so-called Swiss cheese appearance of the brain indicates that mental capacity might be limited. Although the energy of the Tc-99m gamma ray and 140 keV is not significantly larger than the energies of typical X-rays, the imaging setup of SPECT is fundamentally different from that of the more familiar X-ray computed tomography, CT. In both SPECT and CT, photons of similar energies are detected. Can you elaborate the fundamental difference and how this difference affects the image? The medical application of Tc-99m involves a chain of decays. Molybdenum-99 is the parent or mother, Tc-99m is the daughter, the ground state of Tc-99 is the granddaughter, and the final decay into the stable ruthenium-99 proceeds to the great-granddaughter. Chains or sequences of radioactive decays occur if the decay products are radioactive themselves. The decay law for such chains is the Bateman equation. This complicated equation may be understood better if first the most simple case is considered, namely that of a parent nucleus that decays into a radioactive daughter, with a number of N0 parent atoms present at time 0, but no decay products. The two decay constants are then lambda 1 and lambda 2, and the granddaughter, number 3 in the sequence, is stable. This situation is described by the two differential equations indicated here as 1 and 2. The first is the differential equation that leads to the radioactive decay law. dN1 equals minus lambda 1 N1 dt. The second equation involves a production term and a decay term. It is given by dN2 equals lambda 1 N1 dt minus, because that's the decay term, lambda 2 N2 dt. In words, one can say that at any time t, the number of daughters increases, but also decreases because of their own decay. The integration of equation 1 gives the familiar radioactive decay law, as n1 of t equals n0 times exponential function of minus lambda 1 t, which is indicated here as equation 3. The differential equation 2 can be solved by starting with the general ansatz shown here as equation 4, with two exponential terms that include the two decay constants lambda 1 and lambda 2. Proceeding with this most general solution, the decay and activity laws for the radioactive daughter can then be derived from the boundary conditions of the situation. Two important boundary conditions arise for the situation when time equals 0. They are indicated here as I and 2I. Since initially there are no daughter nuclei N2, the parameter A equals minus B. Furthermore, we see that for t equals 0, minus lambda 1A minus lambda 2B equals lambda 1 N0. From that we can derive an expression for B. B equals lambda 1 N0 plus lambda 1A divided by minus lambda 2. Combining with condition I, we find that A is given by lambda 1 N0 divided by lambda 2 minus lambda 1, and B is given by minus lambda 1 N0 divided by lambda 2 minus lambda 1. The decay law for the radioactive daughter is therefore given by the equation in the top box. We can check this result by assuming for the moment that the daughter is not radioactive but stable. Then lambda 2 has to be equal to 0, and the expression in the box becomes an exponential build-up to eventually the number n0 of nuclei, but now in the form of the daughter nuclide. Since activity is always lambda times n, the activity law in this case is given by the expression in the bottom box. It is clear that the activity of the daughter depends only on the initial number of mother nuclei N0 and the two decay constants. Depending on the relative magnitudes of the two decay constants, lambda 1 and lambda 2, three special cases of the mother-daughter relationship can be distinguished. If the daughter decays relatively quickly, in other words, if lambda 2 is larger than lambda 1, an equilibrium situation will arise. If lambda 2 is very much larger than lambda 1, the parent is relatively long-lived, and the mother therefore decays essentially at a constant rate. This means the exponential function e to the power of minus lambda 1t is effectively 1. The daughter activity is then, in good approximation, equal to a naught times 1 minus e to the power of minus lambda 2t. For large times, the activities of daughter and mother are therefore almost the same and constant. This is called secular equilibrium. A different type of equilibrium, a transient equilibrium, establishes itself when lambda 2 is larger than lambda 1 but of similar magnitude. In this case, the ratio of the two activities A2 and A1 is given by lambda 2 on lambda 2 minus lambda 1 times 1 minus e to the power of minus lambda 2 minus lambda 1 times t. This means for large times, the ratio of the two activities is effectively constant. In other words, the activities of mother and daughter decrease in sync. In the opposite case, where the decay constant of the mother is very much larger than that of the daughter is long-lived. In this case, the daughter activity A2 is given by a naught lambda 2 divided by the difference lambda 1 minus lambda 2 times e to the power of minus lambda 2t. This means the mother decays quickly, while the daughter also decays exponentially, but over a longer time scale. The two equilibrium situations are distinguished by the words transient and secular. How would you translate transient equilibrium into your own words? And how would you translate secular equilibrium into your own words? In this semi-log graph, the activity of a mother appears as a straight line A1 of t. The graph compares the two situations that are possible. If the decay constant lambda 2 of the daughter is very much larger than that of the mother, a transient equilibrium is established and the daughter activity follows that of the mother. In the other case, where no equilibrium is established, the decay constant of the daughter is smaller than that of the mother. Lambda 2 is less than lambda 1. In these graphs, all three special cases are compared on a linear scale. In the top graph, the non-equilibrium situation, where the daughter decay constant is less than that of the mother, and activities of mother and daughter follow different time functions. In the graph at the center, the secular equilibrium situation, where the decay of the mother is relatively slow and effectively constant, and the daughter approaches that constant activity, and eventually both mother and daughter decay with the same activity. Finally, the transient equilibrium situation, where the decay constant of the daughter is similar to that of the mother but larger. In this case, the daughter decays quickly, and the daughter activity soon follows the mother's activity, both decreasing exponentially. Using in particular the concept of Lagrange transformation, Bateman derived an equation shown here that describes the situation for more than two sequential decays in general. The parameters of this equation are familiar. For example, n is the number of nuclei of a particular species at time t. Lambda j and lambda p identify the respective decay constants of the nuclides, and each further radioactive nuclide in the sequence adds another exponential term e to the power of minus lambda t. The derivation of this equation is complex, however it is straightforward to confirm that it is valid for the simple cases of single decay, 2 sequential decays, and 3 sequential decays, assuming that initially no daughter and granddaughter nuclei are present. When deriving these special cases, it's important to keep in mind that the summation sign when not contributing a term gives a 0, and the product sign when not contributing a specific term gives a 1. In order to appreciate the structure of the Bateman equation, it may be helpful to write down the Bateman equation for 2 sequential decays, a mother and a daughter, with a finite initial concentration of daughter nuclei. Tc-99m can be produced in several ways. However, in the context of medical applications, it is often produced using a cyclotron. The reaction equation is illustrated at the top left. A proton beam is incident on a stable molybdenum 100 target, and a p-n reaction occurs, whereby the incident proton ejects another proton and a neutron. As discussed earlier, the molybdenum-99 then decays via beta- decay into technetium-99m. However, alternatively, it can also decay via beta- directly into the ground state of technetium-99. A photo of a modern cyclotron is shown at the bottom left. The principle is illustrated at the bottom right. A cyclotron features 2 so-called Ds. These Ds are shown here as dark blue. An ion, in this case a proton, is accelerated across the gap between the 2 Ds. That means the potential difference between the Ds has to be alternating. The ion is kept on a circular path by a strong magnetic field that in this case points upward. As the ion moves through larger and larger circles, its speed goes up until it is eventually ejected at the rim of the cyclotron. Explain, why is the direction of the magnetic field in the cyclotron diagram pointing upward? The transmutation of molybdenum-99 to technetium-99m is in transient equilibrium. The mother, molybdenum-99, has a half-life of almost 66 hours, whereas the daughter has a half-life of about 6 hours. Its decay constant is therefore 10 times larger. The activities of both isotopes therefore follow each other and decrease exponentially. The purple curve shows the idealized case where all decays proceed via the isomer technetium-99m. The yellow curve takes into account that that is not the case, since a certain fraction of the molybdenum-99 decays proceed directly into the ground state of technetium-99. In practice, the molybdenum-99 is produced in a cyclotron facility and then transported to the hospital in a generator such as the one sketched here. Using a 0.9% sodium chloride eluent, the technetium-99m can be drawn from this generator. In the saline solution, the technetium occurs chemically as technetium oxide. The graph shows that it takes about a day to establish the transient equilibrium between molybdenum-99 and technetium-99. The illusion of the technetium medical isotope then reduces the technetium activity, and it takes a further day to reach equilibrium again. The illusion efficiency therefore depends sensitively on the timing of the illusion. The extraction of the technetium-99m can be well timed. It may be too early or too late. That is shown here. In contrast to the previous graph, some inefficiency of the extraction process is also considered. The blue curves thus represent the measured activity of the extracted technetium rather than the theoretical ideal activity. The sensitive dependency of the illusion efficiency on timing has consequences for the organization of treatment of patients in the hospital. Following treatment, the technetium-99, now in its ground state, decays further on to the stable ruthenium-99. Is this decay in equilibrium with the molybdenum-99 decay? Another question one may ask is, why are only traces of the element technetium present on Earth? Shown here are some example answers to the self-study questions in this video. Interestingly, the technetium-99 half-life and also the half-lives of all other technetium isotopes are much shorter than the age of Earth. Therefore, the few traces of technetium found on Earth are due to the ongoing production processes in nature, such as spontaneous fission, or due to man-made medical isotope synthesis.